let's have a look at the first example of the use of a probability tree diagram for problem solving. So let's read through the question together. So a box contains 3 blue and 5 red counters. So I should put some counters there. 2 counters are drawn from the box without replacement. And I think it's very important here that we emphasize without replacement. In other words, we draw 1 counter, we don't put it back. So the next counter that's drawn, okay, the probability of that's going to be a little bit different, okay, from drawing the first counter, okay, because the number of counters would have changed. Calculate the probability of, part A is 2 counters are the same color. Part B, drawing 1 red, 1 blue counter in that order. And part C is at least 1 red counter. So what we're going to do is we're going to draw a tree diagram, and then we're going to use we're going to actually put the probability of each of the outcomes on the various branches, and then determine the final probability of getting the various combinations of red and blue counters. Okay, so let's start off, and actually I might just enter it here. Okay, so first stage, okay, we can draw either a red or a blue counter. So the reds, we've got 3 out of 8, and that's the probability of drawing a red on the first go. Okay, so I'll just put the probability there on that branch. This branch, obviously, well, we've got 5 blue counters out of 8 in total. Okay, so that's the first stage. Notice that with each stage, or if the branches that come from the same point have to add up to 1. So 3 on 8 plus 5 on 8 will give you 1. Okay, so that's actually a check to make sure that, well, at least to help make sure that the tree diagrams are drawn properly. I mean, it doesn't guarantee that you've done it correctly, but at least you've you've sort of done some of your checks and balances along the way to ensure as much as possible that the diagram's correct. So after we draw a red, we can still draw a red, another red or a blue in stage 2. And also, if we've drawn a blue, we can also draw a red and a blue as well. So basically what we're doing is that we're repeating the experiment again. This time around though, we've got now one less counter. So let's say, for example, I've drawn a red. Okay, so how many counters have I got left? There's now 7. So the denominators of the branches in stage 2 are all going to be over 7. Okay. Right, so now if we've drawn a red on the first stage, and the second stage, we've only got 2 red counters left. So we've reduced the number of red counters because of the first stage we've drawn a red already. Now we've only got 2 left. Now if we've got 2 red counters to choose from, we've got 5 blues. Okay, and again, 2 on 7 plus 5 on 7, because the branches come from the same point, okay, the branches must add up to 1. Likewise, if we've drawn a blue, okay, from the box, we've still got 3 red counters left, but this time around there's now only 4 blue counters left. Okay, it's always good. Sometimes it's good to visualize the experiment if it gets a little bit difficult to visualize, but if you don't have any, obviously don't have any issues sort of visualizing the experiment, then obviously the counters are not necessary, but it's just good to see. All right, so I'll just put those away. Now let's answer the questions. Okay, so without the tree diagram, answering these questions will get a little bit, might be a little bit tricky. Okay, so first of all, what I like to do is I like to list all the, I might just put the board up a little bit. Yep, I like to list the various outcomes. So outcome 1, as in the final outcomes, we've got red, red. Okay, we've got red, blue. We've got blue, red. Then you've got blue, blue. Okay, so the probability then of red, red, okay, is that you basically follow the branches and you multiply the probabilities above each branch. So for red, red, we've got, let's see if I can just get that calculator there. Hopefully you can see that okay, just on the side. 3 on 8, okay, and multiply that by 2 on 7, okay, and we've got 3 on 28. Okay, so that's the probability of red, red. Okay, probability of red, blue. Okay, 3 on 8 times 5 on 7. We've got 15 on 56 is the probability of red-blue. The probability of blue-red, again, it's in that order. I'd say order does matter in this instance. We have 5 on 8 multiplied by 3 on 7. We have 15 on 56 again. Okay, sometimes you may get two different outcomes with the same probabilities. And last one, blue-blue, we've got 5 on 8 multiplied by 4 on 7, and we have 5 on 14 is our probability for blue-blue. Okay, so answering then part A, two counters the same colour. We've got red-red, blue-blue. So probability of red-red or blue-blue. You just add the outcomes that are of importance to us for that event. So the event of two counters the same color includes red-red and blue-blue. Okay. So remember that an event is a group of outcomes or a set of outcomes that we favor. So red-red, blue-blue, 3 on 28 plus 5 on 14. Okay. So 3 on 28. 3 on 28 plus 5 on 14, and that gives us 13 on 28. Okay. Something else just to note is that the outcomes, the sum of the final outcomes also must equal 1 as well. All right. So and you can check that, and it will equal 1, but just it's another one of those checks that very important that if you've got time to do, just check that. 3 on 28 plus 5 on 56, sorry, 15 on 56 plus 15 on 56 plus 5 on 14 equals 1. Part B, one red, one blue counter in that order. Well, that's a fairly straightforward one. We want the RB case, which is this one here, which is 15 on 56. So probability of red, blue, and just you can read that straight off the probability tree diagram there at the end. And C, at least one red counter. So in other words, the outcomes has to have a letter R in it. Okay, so at least one could have red, 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 blue, blue, red. There's two ways of doing that. You can either add these three probabilities together, and that's fine, or you could look at the complement of at least one red counter, which is no red counters, which is blue, blue, and we subtract 5 on 14 from 1. So probability of at least one red is equal to 1 minus the probability of blue, blue, okay, which is basically no reds, and that's equal to 1 minus 5 on 14, which equals 9 on 14.